Today, I'd like to go over a worksheet that you're going to do today called What is Energy and How Does It Flow? We're looking at how developing something called bar charts help to make sense of temperature changes that occur when heating water. So go ahead and get this worksheet out. This is the worksheet, What is Energy and How Does It Flow? And I'd like you to follow along with me as I discuss each one of these bullet points at the beginning of the worksheet. So what is an energy bar chart? An energy bar chart shows a system, and it's going to be showing how energy is transformed within a system, how energy enters the system, leaves the system, and what kind of energy we're looking at. Sometimes we call these bar charts LOL charts. You might hear me call them LOL charts because they kind of look like an LOL. And the system has to be written within the O. So in this case, the system is the cup. So you may have a cup, a beaker. You may have the system be the table. Your system might be a hand. Your system may be the whole room. Your system could be the whole earth. You need to define your system when we work our way through these. That's very important. So the name of the system goes inside the O of the LOL. Now, you may have heard before in your life that kinetic energy is the energy an object has because it's moving. You may have learned this in middle school or before in your life. And we're not going to change this definition. Kinetic energy is still the energy of movement. It's just instead of working with cars or balls or rolling down hills, we're going to be working with particles. So kinetic energy, in our case, equals thermal energy. Okay, so thermal energy really is our version of kinetic energy. It is the energy that is stored by the movement of particles. So the quantity of energy is related to the mass and velocity of the particles in the system. So when we look here on the left-hand side, we have a cooler system and the particles are moving more slowly. And as you look to the right-hand side, we have a hot system and the particles are moving really quickly. The energy can be described then, in this case, by the temperature of the system. Warmer temperatures equate to more energy in the thermal account. So thermal energy is kinetic energy. The next type of energy that you may have heard of before is potential energy. And a classic definition would be the stored energy in an object due to its position and or properties. So you can see here in my little picture, I've got a ball and it's showing that that ball has potential energy. You have potential, it's cute, because the ball is ready to move down the hill. So that is based on its potential. We call that potential energy. But in chemistry, potential energy equals phase energy. So in this case, we're going to be looking at if things are solid, liquids, or gas. So energy in this account is the energy stored in the system due to the arrangement of particles and interactions between those particles. So greater attraction decreases the energy of the system. In other words, as particles are more tightly bound or more attracted to each other, the energy of the system decreases. Solids possess the least amount of energy in this account, followed by liquids, and then gases have the most amount of energy. Okay, so potential energy is phase energy, lowest energy is the solids, most energy is gases. So when we look at these LOL charts, they have arrows and blocks that become very important. So you'll see here in this case, it's showing the kinetic energy or thermal energy as having 2 blocks, and then the potential energy as having 2 blocks. My system is the tray of water, and you can see here there is an arrow pointing out that's showing that energy is leaving the system. And that's why I only have 1 block left over here, but my 2 blocks have gone unchanged. So make sure whatever is here equals whatever is here after you've either added or removed things to the system. So the arrows and the blocks represent that energy moving out or into the system. So each bar is made up of individual blocks. Changes in the number of blocks make up a bar from the beginning to the end, show the transfer of that energy in and out of the system. Also, the transformation of energy within the system. So it doesn't necessarily have to, you can have things change within a system without things coming in and out as long as your addition of the blocks works. We're going to use a couple general rules for this. Kinetic energy at room temperature for liquids is going to be about 2 blocks. Now, this is not written in stone. However, in this case, you can see the kinetic energy or that thermal energy increases. That means that whatever this was, this cup, went up in thermal energy. The temperature went up. And you can see there that this temperature went up because this block was brought into the system. So there's the temperature going up. Now in this case, the phase energy or potential energy did not change. The phase energy is the same. Now these we do have a hard, fast rule for. Solids are represented by 1 block, liquids are represented by 2 blocks, and gases are represented by 4 blocks. So you can see here that this is discussing a liquid. It started as a liquid, it's ending at a liquid. Now you might be asking, why is it 2 blocks to 4 blocks? Why don't we use 3 blocks? Well, we learned before that solids and liquids, their particles are pretty close. They have some things in common. But a gas, the particles really spread out and their particles are moving quite a bit. So a gas is very different. That's why we jump to that 4 blocks. So as you look at your worksheet here, we're going to look at the first example. It says water in a cup is heated from 20 degrees Celsius to 80 degrees Celsius. Now you'll notice here that I'm going to go ahead and draw these particles on the left and the right. I want to make sure that I remember that they are water. I want to keep the particle count on the left the same as the particle count on the right. And I want to show somehow that the temperature is increasing. So I'm going to go ahead and do that with arrows. See on the left there, I have short arrows. On the right-hand side, I'm going to put larger arrows to represent more movement of particles. So it is still water before, and it's still water after, but I want to show there that the water has changed from 20 degrees to 80 degrees by having faster moving particles. Remember, this is the kinetic energy, and sometimes people will draw this with these little kind of wiggly lines. So you might have like small wiggly lines for a lower temperature and bigger for a higher temperature. Always remember to also say what your system is. That was in a cup. Let's look at the next example. Liquid at 0 degrees is turning into ice at 0 degrees. So you'll notice here that our potential energy is now changing. Potential energy on the left is liquid. Potential energy on the right is ice. So we're going to lose a bar. So the kinetic energy is actually staying the same, but the potential energy is changing. See, 0 degrees to 0 degrees. Potential energy has 1 block leaving the tray. So this tray is showing us here is what is our system, and I can count before and after to make sure I have the right amount of blocks. So when I draw the particles, I want to have liquid in my first drawing, and then I want to make sure I have solid in my second drawing. I don't want to change the number of particles. In this case, I counted 7, so I want to keep 7 at the beginning and 7 at the end. Now, in order to show movement of particles, because these particles are moving, I should have arrows, and the arrows on the left-hand side should be about the same size as the arrows on the right-hand side, because the temperature has not changed. It's 0 degrees turning into 0 degrees. So for each of the situations described below, use an energy bar chart to represent the ways energy is stored in the system and flows in or out of the system. Below each diagram, describe how the particle position and particle motion change from the initial to the final state. So particle position and particle motion. Good luck!